All right, now we're going to continue classifying groups up to isomorphism. Now we're going to classify groups of order 12. So we already saw from the application of CELO theory, we looked specifically at the case of 12, and we determined that if you had a normal there was a CELO 3 subgroup because 12 factors is 4 times 3. And what we had determined at that time was that either P was normal in G or G was isomorphic to A4. That was something we had proved. In fact, in more generality, we had looked at groups of the order P squared Q, and we had determined that either you had a normal Q subgroup or that normal P squared subgroup. And in one of the base cases, you ended up with 12. And in that case, we had more information. Now, it's important to note the book focuses on the case of 12 here instead of P squared Q for a reason. There's actually, the classification of groups of order P squared Q is actually slightly non-trivial. I'll indicate what it is at least a little bit in a moment, but I'll focus on 12. So we'll follow the book, and in the book they focus on this approach instead of this one. So I'll do this two ways. First, I will actually just take advantage of this fact. So we're in two cases. Either you have A4 or you have P is normal in G. So let's assume that P is normal in G. Remember, P has order 3. And note, of course, that a CELO 2 subgroup exists. And, of course, its size is 4. And so, because P is normal in G, P times G is, in fact, a subgroup. And its size has to be 12, because 4 and 3 have no common factors, so in fact it's the whole group. And likewise, P intersect Q is the trivial group. And so we see, in fact, G has to be isomorphic to the semi-direct product of P with Q. And in particular, G mod P is Q. So any group in this case must be a semi-direct product. And so the point is that the classification of groups of order 12 up to isomorphism turns into the classification of semi-direct products of a group of order 3 with a group of order 4. Or you get the alternating group. Those are your only two cases. Now, there's a reason why the book focuses on the particular values it does. This doesn't always happen, and maybe I'll at least include one case where you get more than just semi-direct products to illustrate why the isomorphism problem in general is hard. But when you're lucky and you only get semi-direct products, the classification gets a lot easier. So let's see what happens. So we've seen that if your CELO 3 subgroup must be normal in G, you must be a semi-direct product. So let's classify the semi-direct products. Well, they must correspond to homomorphisms from Q into the automorphism group of P. And here Q is order 4 and P has order 3. You obviously see the slight issue here is that there's actually more than one group of order 4, so we actually have some cases we have to worry about. Note I'm not following the book exactly because the book is using notation T and V here, but I'm being consistent with the P's and Q's we were using in CELO theory and the P's and Q's I was using in the last video. I want to remain consistent with that for all the examples. Although I have to admit, if I was more consistent, I'd always make sure Q corresponds to the larger prime. So it should be Q for 3 and P for 2, but I'm sorry about that. Alright, so case 1. I think I usually focus that P is always the prime I find more interesting. So in this case, 3 is more interesting. Q is Z4. Note, ought P here is isomorphic to Z2. P is a cyclic group of order 3. So let's say it's generated by A. The only non-trivial automorphism is the one that sends A to its inverse. And then the identity automorphism. And so what can phi do? Well, Q has to be generated by something. Let's say it's generated by B. Well, it's an element of order 4, and the only automorphisms either have order 1 or 2. So you only have 2 choices. Either phi of B is the trivial automorphism, or phi of B is this inversion. So that's a case 1A and a case 1B. Well, in case 1A, what happens? Well, that's the case where whenever you get the trivial automorphism, you actually have a direct product. Which means that you have the direct product of Z3 with Z4. Congratulations, you have Z12. I'll come back to this other one later. It turns out that it's a new semi-direct product, unlike anything we've ever seen before. So it does not turn out to be some sort of dihedral group thing. Unless it does. That's a good question to ask yourself. So it's worth pointing out the other case was when Q was the Klein 4 group, Z2 times Z2. Well, this has 2 generators. Let's call it B and C. And naturally, there must be a kernel, any automorphism here, homomorphism here. Has to have a non-trivial kernel. And so I did an example like this with the groups of order 30. And something similar should happen. Either you're going to have 3 possible homomorphisms or automorphisms. Either phi B is going to act by sending A to A inverse and fixes phi of C fixes A. A slightly different phi fixes A, while slightly different phi of C inverts A. Or finally, there's the final choice, which does inversion in both cases. These are 3 different non-trivial automorphisms. But you can check that they're all going to give the same group. One reason why is because, well, suppose I picked this one, then up to a change in basis, these 2 can be derived from that one, namely because what can I do? I can define, okay, let me think about it carefully. Well, it has to do with change of variables. The point is that while this group is generated by these two symbols, technically any two of the non-identity elements generates the same group. In other words, the automorphism group of C2 cross C2 is pretty interesting. For instance, if I suddenly decided to define B prime to be equal to C and C prime to be equal to B, then I have a new generating set, and on this new generating set, I could define the primes of the variables to be phi of the prime variables, and you discover that phi prime is capital Phi. Likewise, I could define B double prime to be B, and C double prime to be C plus B. And you can check that if I do the same trick to find phi double prime of the variable to be phi of B double prime, and phi double prime of C to be phi of C double prime, you can check that phi double prime is pi and is still an automorphism. It's a very weird case with the Klein 4 group that you might recognize if you've ever spent enough time dealing with this group. So with some of the undergrads, I often look at it as the symmetries of the rectangle, and the point is that if you add any two of the elements, you get the third element. So in some sense, up to change a variable, which means up to an isomorphism on Q, these automorphisms, this homomorphism, is the same. So the resulting semi-direct products you're going to get are all going to be the same group. This isn't a complete formal proof. It's just an intuition that you're going to get the same group. From these three, there's still a fourth homomorphism, which is the trivial one, which is that all the elements fix A. That's going to result in the direct product. The point I'm trying to say imprecisely about these three maps is that they are similar in the same sense that you talk about matrices being similar. In other words, they're equal up to conjugation by an automorphism of Q. And something you can prove is that when that happens, the resulting semi-direct products are also isomorphic as groups. And so even though there's three different homomorphisms here, they're all going to give you isomorphic groups in the end of the day. So later, I'm only going to consider one of them. So what have we gotten so far? We got A4. We got these two direct products. And we got these two semi-direct products. Now, one question you might want to ask is there an easier way to describe these two semi-direct products? Why would you want to do that? Because, well, sometimes if you can replace semi-direct products with direct products, it's a little easier to work with. So let's look at this one again. So what happened here? Well, we had our element of order A, whose cube is the identity, our element of order B, whose fourth power is the identity. And remember this homomorphism must send phi of B to the automorphism of order 2. which means that BAB inverse is A inverse. This is definitely not the dihedral group and looks nothing like it, so this seems to be an actual new non-trivial group. To convince ourselves that this isn't the... So my point is, one of the guesses was, is this equal to, say, Z2 cross D6? And it's starting to look like the answer to that might be no, because I don't see how to get this in the usual format. So one way you might want to figure out how to show that that answer is no is to actually look at the subgroup structure here. So D6 is the symmetry group of the triangle, so it has a 3 cycle. So when you multiply here, you have an abelian group of order 6. Here, do you really have an abelian group? Yeah, it looks like you do also have an abelian group of order 6, so that's not the contradiction, is it? Ah, now I know what the contradiction is. Here you have an element of order 4. Duh, because it's C4. You're not going to get an element of order 4 here, because this is every element that's not of order 3 is a reflection that has order 2. And every element over here that is order 2 or 1, you're not going to get an element of order 4. So these are definitely not isomorphic. This is really a group that can't be expressed any other way. However, this is a well-known group, and it's not on our list so far. So process of elimination, this group must be isomorphic to this one. Let's see if we can actually see why. So we had A, B, and C. A cubed is the identity. B squared and C squared are both the identity. And I guess we're going to decide that BAB inverse is A inverse. And AC and CA commute. It's one of those 3 automorphisms. The one that where phi of B applied to A is A inverse, but phi of C applied to A is A. Well, since A and C commute, we can see here that A times C should have order 6. And BACB inverse here gives you A inverse C, but C has order 2, so it's its own inverse. And by commutativity, you can write that in the other order. So then you could say that you got AC inverse. And so look, you have the standard presentation, one of the standard presentations of D6 here. It looks like, sort of. In fact, you've gotten even farther. Isn't this D12? Why, yes it is. So D12 is isomorphic to this group and this group. Now one can ask about P squared Q, and I might give a link to this if people are interested, because it actually gets pretty hard very quickly. But I will at least indicate the start of the process. So it turns out you end up in these 2 possible cases. Where either P is normal in G or Q is normal in G. And naturally, in either of these 2 cases, because there ends up being a CELO subgroup of the opposite size, you can prove that whatever group you get is a semi-direct product. So no matter what, either G in this case is a semi-direct product of P with respect to Q, and in this case, G is a semi-direct product with Q with respect to P. And obviously there are cases where it's just a direct product. And so in this case, it turns out that you're looking at all the possible ways that you can find an automorphism from Q, a homomorphism from Q into the automorphism group of P. And over here, you're classifying all homomorphisms from P into the automorphism group of Q. Q has power 1 here, so this is a cyclic group. The only issue, of course, is it's not clear what P is. P is either Z mod P squared or ZP times ZP. And that makes that part of the argument a lot harder in general. Namely, you look over here, and this is order P squared minus 1. And so the only way for there to be a non-trivial automorphism is to have Q divide P squared minus 1. On the other hand, over here, the group has size Q minus 1. So over here, you would need P to divide Q minus 1. So P squared factors as P minus 1, P plus 1, and since Q is prime, that would imply that Q has to divide one of these. So you see very different criterion here, and this starts to tell you some information. On this left-hand case, nothing interesting happens if Q is really big. Because if Q is too big, this divisibility can't happen. Whereas over here, nothing happens if P is too big. So over here, the only time this is non-trivial is if P possibly non-trivial is if P is less than Q minus Q. Similar over here, it's only possibly non-trivial if P is greater than Q. Ignoring the cases where P is 2 and Q is 3, because that's the case we already covered. In general, these are the more interesting cases, and I think the article I can link to focuses on one of them, and you quickly discover one of these two setups they look at and nothing interesting happens. It's the other setup, I think over here, where all of a sudden they get lots of groups. And there's a reason that article focuses on that particular case, because it turns out on this case, nothing that interesting happens. And the reason why that is because P has two possible choices. P is either ZP squared or it's ZP times ZP. And it turns out stuff with ZP squared is not that interesting, but the automorphism group of ZP times ZP is a matrix group. And so there the classification gets a lot harder, and you end up with a lot more possible semi-direct products. Whereas over here, the automorphism group of a cyclic group is, well, it's still just modular arithmetic, just with multiplication. So it's not a very complicated group. It doesn't have that many subgroups of different orders, and so it turns out this classification is much easier. For those who are interested, I will link this paper, but I will leave it to you to figure out this classification.